Hello everyone, this is Treton and I'm gonna try to do the voiceover for the kernel development video. So this is a English version of a Spanish video, so I will try to watch what's on the screen right now and try to explain it as best as I can. So here I'm gonna tell you about the series. The idea is to start from the beginning, from scratch, from an environment that we will set up together. And as you can see, there is an earlier version that uses BIOS instead of UEFI. So this video is also available. This is also in Spanish. This won't have a voiceover, but you can check it out and try to figure out how to create a bootloader from scratch. That's an interesting academic project, but right now what we are gonna focus on is on creating a bootloader with UEFI support for native 64-bit architectures, and this will be based on the project that you're seeing right now on screen. It's called Bloodmon. This is the label is Cool Kernel with pedantic name. So this is a project that I did this summer, and it covers from memory management to processes. Device driver, a device driven interface, and how to manage the basics of some hardware. So this repo will be linked on the description. You will have everything that you need to start up your development environment. And right, so let's see the structure for this series. In this first video, we will create an environment to work under Windows. You will use Windows Subsystem for Linux, and basically that's it. You will use QEMU to emulate this hardware. Right now, where I'm telling is that you have the code for Blood Money on the repo, and you have a tag attached to every milestone that I make. So you can go like the first tag, it's memory. So you will have there the page frame allocator, a basic memory statistic module, and perhaps a little bit of virtual memory. You will have another tag that is called SMBIOS. You have the structures required to parse that BIOS structures and get some info, and that's basically it. Right now, I'm not sure what I'm saying here. Let me get here. Okay, right now I'm talking about the WSL. So Windows Subsystem for Linux is just a full Linux kernel supported inside Windows that we will have to install to make this work. And the idea is really simple. You just go to add or remove Windows features, and you will set the following options that you will see right now. So there it is, and these features are in Spanish, but basically what you need is to disable Hyper-V. You need both options disabled. You will also need to disable, I'm not sure how to say, protected space. You have to enable for sure Windows Subsystem for Linux and virtual machine platform. That's basically it. It will probably still work without the isolated space, but you will have to disable for sure Hyper-V. You will have to enable Windows Subsystem for Linux and the virtual machine platform. So do it right now if you want to follow up with me. And after that, you will have to install the distro that you want to work with. I will work with Ubuntu, so just open up a terminal. By the way, there is a improved version that I'm not sure if it's already shipped. It's already being shipped with Windows 11, but you are also good if you use the basic PowerShell. But if you want the advanced terminal, that is, I'm pretty sure it's already included with the latest versions of Windows 11. But if not, you just have to open the Windows Store and search for Windows Terminal. You will install the app and you will have it available in a few seconds. So just boot it, and you will be welcomed by a PowerShell window. So with that, you will have to open it as an administrator, and just let it zoom quickly. And as you can see, we are using our local user. So just type the first command that you can see on the screen, wsl minus minus install, and it tells me that it is already installed, but you will have probably no distros ready. So just select Ubuntu that you want to install, or everything that you need, and with that just copy the command that you're seeing on the screen. Okay, you will get a list of available distros, and just make the wsl minus minus install space minus d and just paste the distro. That's basically it. You can follow up. You can do it while you're watching this tutorial. So here you can see the command wsl minus minus install with 2ls minus d and the distro that you want. I have already installed Ubuntu, so that step is already completed. And let me clear a bit. Okay. Okay, you will have the link for the WSL related data on the description. Also, you can type it now WSL. You will be welcome with your usual Ubuntu terminal. This will be usually bash, and you will be asked for creating the initial user. So it is really easy. Just tell the username, the password that you want, a bit about is this the country, the location. You can set that to a default value. It is really easy. If you install any Linux distro, you will already know the steps. So when you have this kernel, you will see that it is a native Ubuntu, that it is working on a custom kernel, that it is based on the Linux 5.10.16 right now. Well, I'm recording this the 6th of October of 2022. I'm not sure if you used that format for years over 1999. And let's see. So what I'm telling you right now is probably about the mounting point. So you will have access to your drive from WSL and vice versa. So you can just go to /mnt/c to get to your C drive from Windows, and you will have also your usual Linux directories. You have your etc, your var, your home user. Everything is where it should be, but also you will have mounted every drive that it is available to your system, and also it works both ways. So you can type backwards slash, I'm not sure how you say, but you are watching on the screen, WSL, and this is a typo. Just to go $WSL, or in this case is WSL dollar, maybe. Yes, WSL dollar. So you will have here a folder for each one of your distros, and you can just go and double click on Ubuntu, and you will see the entire file system available for you. So that's pretty much it. That's how you interact between Windows and Ubuntu. You will have a few restricted operations, and you will have to pass always through your Windows hardware. WSL kinda interacts directly to bare metal, but it is always bound to the restrictions that Windows imposes. So you will have, let's say that you want to connect to the internet, you will have to connect through Windows. You cannot get direct access to your network card, for example. So with this, let me check where we are at the video. Okay, we are gonna create the folder. Just create the folder that you want. I will call it tutorial YouTube, and this is a working directory. Just cd inside it. Well, I already had a a folder called tutorial, and you will see this is an empty folder. We will use for the ID, let's say for the text editor, Visual Studio Code, so you can install it. But you can use whichever you want. In this case, it just puts when you type code space dot, so you will see that, well, it is kind of hidden by this Twitch subscribe screen, but you are connected directly to the WSL machine, so you are not going through Windows, and this is your text editor. Just install now the dependencies. I mean, for development purposes, you will need a few tools. Are really simple toolchain, and for installing it, you can follow the post that it is attached on the description about how to install GCC. This is pretty much the only dependency for compiling. We won't compile assembly right now. In next videos we will do it, but I will tell you how to install NASM. But right now, just copy and paste the commands that you're seeing on screen. You will need the dependency on build essential. You will need probably not man pages dev. This is just to get some documentation, and with that you can invoke GCC minus minus version, and you will see. I'm not sure the dash is correct, but you will see that we have a GCC. Actually, about let's talk about the elephant in the room, cross-compiling. So what is cross-compiling? Cross-compiling is just having a toolchain that is aiming to create software for another architecture. Right now we won't need it. We don't really need it. So why? Because our target architecture is just Intel x86 on 64 bits, and this is already our source architecture. The only difference will be the AVI, but we will try to maintain it. AVI is just the calling conventions that our software follows. So that should be not a lot of trouble with it. Eventually we will start to see weird errors like our program. We told the program that we want to, let's say, make a subtraction, but the program will make a division, let's say, and you will see that if you object dump the software, you will get a different result than if you disassemble it through the GDB. So this will be probably a toolchain error, and you will have to start creating the course compiler. It is not really that hard, okay? So you just copy the code for GDB, GCC, let's say LD, and you will give it a few flags and let it compile. It will take a really long time depending on how powerful your computer is, but it is not that hard. We will cover it in a following video, but right now you don't need. So you have now to install QEMU. QEMU is the emulator that we will need for this tutorial, and just go to the page, go to the downloads, Windows, select 64 bits if you are running a 64 bits machine. If not, just buy a new computer and download the installer. It is your average, your basic Windows installer that is next, install. And that's pretty much it. It is really easy. It will generate you a folder. You can see on the left bottom margin of the screen that it is downloading already. So it will create a folder on C program files. And okay, so you can see it is really easy. Just next install. And it will install under C program files QEMU. I already have it installed, so I will cancel it, but you will have to proceed with this, and just navigate to this and make sure that the path exists and that the binaries that you will need are present. So these are all the architectures that are supported by QEMU, and you will use QEMU probably x86 underscore 64. That's the one that we will use. And this is executable. We will call it and pass it our image, our kernel image that we will build. So for this, you will need to clone limine. This is the bootloader that we are going to use. The bootloader is just the code that first boots when the UEFI runtime services boot service, sorry, end. And for that matter, just go under your tutorial folder and git clone it. Actually, it would be probably better if you just git add submodule for this. Right now I'm not doing it, but we will do it in the second part. It doesn't really matter. It's just more convenient, but there is no difference. So limine is just a really cool bootloader that will expose some really needed service for interacting with the computer hardware. So you will need, after having installed limine, the OVMF firmware. You can download it from the Ponchos repository. So this is a pre-compiled version that will work really good. So you can build it from the Tiano core repository, or you can just download it from Poncho clone. From Poncho repository. It is on the description also. Just go git clone or git add submodule, and you will have it on your path. Really easy. Just make sure that you have these dependencies. This is just the firmware for UEFI that you will need to run Limine in your services. So with all that, let's say what I'm gonna do next. Perhaps I'm gonna start coding. I'm not sure. Yes, probably I am. So we'll have to create a source folder. A bit of a mess up. And a folder for our builds, and also a makefile. Actually, I'm not gonna use a makefile. You will see later that I will clone the makefile that I use for Bloodborne because it is really complete. A link script that will have a name error, and a build script. I'm not really gonna use the build script, so you can go without it. But everything else you will need it. It will be just convenient to have something that enables you to, let's say, clean, build, and run in one command instead of three. That will come handy when you will have to build 1,000 times per day, but right now it is unnecessary. So on a folder for the source code, we will eventually code everything that we will embed on this tutorial, and just Limine and OVMF as dependencies. The build directory is where we will generate our ELF file for the kernel and eventually the image. The link.ld will define the regions that will make our kernel. Let's say, well, I will talk about the linker later on. Makefile is just a way to talk with the build chain, the compiler, the linker, and tell it on a structured manner how to build the code that we need, and also to automatize the testing phase. And after that, let's talk a bit maybe about Limine. So Limine works on a pretty unusual way. It will have a few it has an interface, a .h file, that exposes a few functionalities that are defined on the Limine protocol that is attached on the description actually of the second video. But a few interesting ones are how to get a frame buffer, how to get a few diagnostic information like the bootloader version, how to get a terminal, how to get let's say the memory map of our kernel. And for this, just go ahead and go to the directory where you clone Limine, and copy the file limine.h and paste it on your root source folder. It is really easy. Just go to the Limine folder, copy the limine.h file, and paste it on source. That's basically it. So with the limine.h file ready, go and create a file called limine request.h, and let's start programming. So the first thing that we will do probably is create an include word. I'm not sure if I'm gonna give a more theoretical approach, but probably not. Let's go and start coding. Okay, so an include word is just a way to avoid headers being included more than once in the same code. So when you do the macro hashtag include, the preprocessor will just copy and paste the code. So if you go and include code twice, you will have two copies that will conflict between each other, and doing this you will make sure that only code gets included only once, because the first time that it is included it already defines that underscore limine underscore request underscore h, and the next time the if not def will be false. So we are creating a few defines for each one of the services that we will request from the bootloader. So they are the bootloader information, the terminal for read and write into the screen, the memory map. Let's see, to the left on the define you will have the key name that will make a reference to the service, and to the right you will have a limine specific references. So you can see the limine.h, and you will see that the requests are named that way that we are seeing. Just we are translating into a little more convenient form. So basically the kernel is just the kernel address, the RSDP is the root, I'm not sure, root system descriptor pointer. It is just a reference for PCI devices. SMBIOS is diagnostic information from the BIOS. You can get it. You can get, let's say, the number of processors, the frequency of them, the number of memory installed, the BIOS name of manufacturer. I created a library for handling all of this that we will use eventually. So let's just create the definitions, and let's say what we are gonna do next, or what we are talking about on the original video. Okay, so with this we are talking just about the modifiers that we are creating for this var. It is really easy. Just static makes sure that the values persist on memory through executions. Volatile just tells the compiler to not optimize because there might be an interruption or something out of the usual execution pipeline that may change the value of this. And just okay, so we are creating a terminal. This is one of the things that you will expect to be later on the kernel development steps, but it is really important to make it right away because you need inside the debugging. And terminal, the capabilities to print values real time is really important. We could create a serial driver, but it will be harder than just to implement a terminal. So just create a structure for your terminal request, and you can see here that this is the weird limine way to interact. So you just create a structure with the request, and you start it with the default values. That this is the ID that it just is. In the end, it's just a number that defines which request we are creating, and a version, a revision that it is always 0 basically. And the bootloader will search for these structures on memory, and if it finds them, it will invoke the expressions and create a structure for the response associated with this request. So we will access these structures that we are declaring later on after boot is completed, and we will see that we have a field called response that will contain the pointer to a response structure that will have the data that we are requesting. So in this case we are creating a request for getting a terminal. The response will be a terminal descriptor. We will have a request for the bootloader info. It will contain a response that will have the bootloader name and version. The memmap request will have a response which contains every memory region. We will see about it on the second video. The kernel address will just have physical and virtual addresses for our kernel, and probably will have RSDP and SMBIOS requests also. We will use them later on. So we are gonna get the RSDP request just as we saw it. You can just program it as you are watching this. It will probably work. This is the best way to follow the tutorial, just to write along. So we are coding the sm values request. And also I will take this time to let you know that this is not a series that you may take for granted. So I'm doing this because the first video had a good reception. So if this gets a good reception also, especially the voiceover in English, I will voice over the second part. So just let me know in the comments, hey, I watched it on the English version, please make the voiceover on the second video and the followings. So right now we are seeing we have created a file that is called bootservices.h. We will create our include word just as we saw earlier on the limit request.h, and this file we will use it to interact with the kernel. This is a really cool trick. We will just make functions to get the data that we need from the bootloader without having to talk with limine. This is just an abstraction layer. So we'll include a standard integer. This will allow us to use UN64 underscore t types, or UN64 8 underscore t. These just are integer types, and we will include the bootloader headers, and we will create the template for the functions that we are gonna code right now. So the first one is just get bootloader name. It returns a char asterisk or a string. Get bootloader version. This returns an UN64 underscore t. This data type comes from the standard integer.h that we included earlier. Get terminal count, because we will have various terminals available. Get current terminal to discriminate which is the terminal that we are working with. Usually it's terminal 0. Let's see what we are gonna do. Set terminal. Okay, we will have to specify a function to change the terminal we are working with. We just specify the number of the terminal, and we will start working with one of every that we have available. And perhaps we are gonna start implementing these functions. Not sure. Okay, so we are including first of all our bootservices.h, our probably limine.h or limine request.h, and with this, okay, so the default terminal will be probably 0. Okay, just to have it on a defined instead of actual memory. And we will have a global variable. And disclaimer: be really careful with global variables on a kernel. They are really spooky because they are not thread safe. We'll watch about it, learn about it. We talk about multiprocessing. So we are going to define a default terminal, and we are defining a global variable right now that it is the current terminal, that it is initialized to the default terminal writer or 0 in this case, and it is just an UN64 number. It will probably be better being a UNT8, but there's no problem with this. So about this, we will have an example or limine bare bones. That is just a simple code that implements the limine protocol. You can see that here they use the request, and in this case they have an element of that request structure that it is not initialized by us but the bootloader, that is called response. So the response just has a few fields that are defined on the limine protocol specification, and in this case we are going to use this example as our main gateway for the implementation. So we have the request, the bootloader will watch it, search for it on global memory, and in this case it will attach the response. So we are gonna define our macro. This will be probably moved to the .h maybe, I'm not sure. So call services is just a wrapper for x.response. we'll pass it an structure. It will return the response associated with that structure. So we're starting with get name, get bootloader name. Copilot is helping us heavily here. And for this matter, we are watching right now probably the limine.h. Yes. And we want to find out what the response value for get bootloader information is. So we are watching, scrolling through it, and we are searching for it on the browser. Bootloader name. Okay, so I found it. It is info response, so it has to char two strings that are name and version. So in this case, we have our limine bootloader info request that will have the attached response, and the response file will have a revision that will be 0 also, and two fields called name and version. You can see that name and that version fields right there. And on our boot services, we will just go and return call service to get the response of, in this case, bootloader. This is the macro that we defined earlier on limine requests, and that makes a reference to that limine name. And this will return the field name. So in this case, it will be better if we just move the call service macro to limine request underscore h, because this way it won't know, boot services will be our kernel code and won't know anything about limine, so it won't know that there is a response field and the fields are called name. And okay, so I found a little bug there, change struct to struct and we will get the function defined for getting the version. This is really simple code, as you are watching. This is not anything advanced, just doing it in a structured way and making good use of abstraction layers. So let's get current terminal. So this just returns that terminal right there global value that we defined earlier. This doesn't talk to limine. And we'll have to start coding the terminal associated functions. And for that, we will have to create some function pointers. This is kind of a spooky topic, but it is not that hard once that you understand it. It is just kind of difficult on a conceptual level. So in this case, this function is just a setter. If you programmed in Java, you know what a setter is. Just you have a value and you don't access it directly, but you have a function that sets it for you. This is really simple stuff. Just code it with me, and probably we will start creating that function pointer. So a function pointer is just a pointer to okay, no, probably. Okay, so we are talking about, this is something else. We are gonna talk about halting and panicking our kernel. Basically, what we are doing here is creating a function that will loop infinitely. That's what the halt function does in assembly, and this will be a error control function with, in case we find an error that we cannot avoid. We don't want the machine to crash, but we will want it to stay in the state that it got the error for making it easier to debug. So with that, let's create our get terminal count and return call service terminal count. Well, terminal, in this case, the value is terminal count. Okay, so we are gonna check if our terminal writer, our requested terminal writer is greater than our terminal count. Because this is earlier initialization and we cannot print an error, let's just halt that machine, make it jump to itself. Let's start an infinite loop, and let's set our terminal writer to the index that we are that we provided it. So this just updates that value in a controlled way. And right now, let me hear what I'm saying. Okay, right now I'm talking about the function pointer. So what we want is to get the function to write to a terminal. That function is provided to us by a function pointer, and the syntax is kind of quirky, but it is not really that advanced. You just have to define it like a regular function, but add an asterisk in front of the name. That's pretty much everything that you need. So in this case, we are creating a generic terminal writer. This is our writing function template that will receive a string that is constant and a number that is the length that we want to print from. So we'll specify the char and the string and the length of the string. We don't necessarily need null terminated strings here. And with this, we will create a pointer to the template of this function. So we will create a pointer to a function that returns void and receives as parameters a const char asterisks and an uint64_t value. So with this, we are going to implement this function, and it will access the limine terminal where we have it. This is just a type. Okay, it is defined here, and it just has rows columns, a frame buffer, and a callback, which is what we need. Okay, you can see the function write. We'll call it. We will get it from the call services terminal / the field is terminals. Okay, these are array of terminals that we will index by the current terminal. Okay, and with this we get from every terminal that we have available the terminal that we specified when we did the set terminal writer. By default, this is the 0, the first terminal. So with this terminal, we will just call write. This is the writing function, passing it the values that we provided to this function. So you can see that the terminal response has okay, terminal in lowercase, please. Okay. Oh, the syntax is different. So we have to provide a terminal that we get from the first instruction of this function, and after that the syntax to call write is providing the terminal. You don't have to go terminal and having a function called write, but you will have a function called write that you will provide the terminal to, and also the string and the length of the string. So this is just syntactic a syntactic quirk, but this is how you interact with it. And for that, this is our generic writer. We will just have to get a way to abstract the way that we generate these writers. Perhaps we'll have to create the function pointer right now. Void. Okay, so yes, we are getting the function pointer. So you see that we are just gonna get the name of the function inside parentheses, and with an asterisk inside the parentheses on the left of the name. And after that, we will just have to set the type. So this receives a string. This is a constant char asterisk, a pointer to a constant char, and a uint64. And with this, you will have the template to our function pointer function, a function pointer returning function. This is kind of weird even to say it. and the implementation for this is really trivial. We will just return our generic terminal writer. So there is no variable called generic terminal writer. This makes reference to the function that we defined earlier. So when we call getTerminalWriter, we will return get the function that we programmed earlier. This allows us to implement our own terminal writers that are not the generic one. We can even store them in an array and index it by any value that we want. So for this, we will create our kernel.h file probably. Yeah, a kernel.c. We don't need a .h for this. And we will include probably our. Okay, so we have made a cut there, and we are gonna include our probably our limine requests. No, but services.h. Not sure if our limine request will be included also. For this, well, we are talking about the makefile. So here I'm gonna tell you probably that your own makefile is kind of hard. So just and it is really uninteresting. So just download the one that you have on the repository and the Git repository. And with this, just modify a few things. So this is for Bloodmoon. This is a kind of big makefile, but it is split on different parts. So we will use this build image experimental way. We will have to specify exp, and we will have to create a few folders. Actually, you don't really need this. You can skip this because there is an instruction that it is called make setup that creates everything for you. It even clones limine for you, so you can just download the make file and go make setup. It will create the environment for your development, and just go make exp, and it will pretty much do everything for you. You will have to modify these values because these are specific to my machine. So you'll just have to replace this with your QEMU, and it is just the path to your program files, QEMU and QEMU x86 underscore 64. You will probably have the same path as I have. But if you have it installed on another drive, let's say it's called D or program files x86, let's say, you will have to modify this to match that file. For this GDB, I'm using the cross-compiled GDB version, but you can just go with GDB. It can be just called under /use/b and /gdb, or probably just GDB without the root. For finding it, you can just go with which GDB. It will tell you which is the default path for the executable, for any executable. And as I already told you, you can go with just the command. And probably mount this, you won't need it. You can erase this tag that is making reference to Bloodmoon, but right now you don't need this. This is just used to make the GPT version. Yes, there is a GPT version. Everything else is just left as you downloaded it. There are a few bugs here that we will fix together, but for now I think this is enough. You can change the version of limine that you're using it. I'm using the version 3.0. The version 4.0 has already been released since the creation of this makefile, but not sure if it's worth it to update. So just delete that makefile and go with the GNU makefile. Not sure if you need to install anything to use GNU makefiles. If you find any errors, just let me know in the description. For this, we are gonna create a file called debug.gdb. Also, you don't need this. You can skip this part entirely because actually, if you make setup, it will create everything for you already. So just go with make setup. It is way easier than to code this yourself. And the debug.gdb file is just being able to attach a remote debugger to QEMU, because debugging another machine, and this is basically a machine, is way different than to debug a local code. So for this, just go with make setup, and it will create everything for you. The command to clean your environment and delete everything is just make clean setup. Clean setup is all together. So in this case, there is a problem because the limit directory already exists, and you can go delete, and yes. And for this, just go again with make setup, and it should work now. Okay, you could see that it is cloning, and it has successfully created everything that we need, and it has created that debug.gdb file and also the folders that you'll need, and a base image for speeding up the creation process. And in this case, you can see that it is connected to an IP. This is your WSL IP, because this will be called through Windows, not Linux in this case. QEMU is a Windows executable, and with this you have your entire environment ready to make your first build of the kernel. So it will fail, of course it will fail. Okay, so we need the linker. This is kind of a boring step, but this is really important. So linker is just a way to tell the program how to lay itself in memory, how to define the layout. And the layout is, I will talk about this while I am coding, because this is kind of a boring thing that is not that important right now. So you can just watch the screen, code as long as you are watching, and hear my voice as I give you the theoretical explanation. The output format is, well, let me talk about ELF. ELF is extensible unlinkable format, no, executable unlinkable format. It is the default format for executables in Linux, and it defines symbols, sections, and I'm not sure how it works. Sectores and sectors. Okay, so sectors. And what we are doing here and now is just defining the architecture and the format that we will want our program to be outputted. So we are talking about an ELF of 64 bits for x86 machines, and the architecture is based on the Intel 386 processor, and our entry symbol, our entry function, will be called _start. So our function on the kernel.c that will be the first to execute will be called _start. This is just analogous to the main function on an executable in user space. And for this, we are gonna set a few sections. Sections are just regions of data that will be logically grouped. So we will have a section for the text. This is the source code, the compiled code. A section for read-only data, that is data that will be only read from, and data that will be written and written to. So we'll have our text section, and it will be of type ptload. This just tells that this should be loaded into memory from the disks, and the flags section that you're seeing there is just assigning the permissions. So the first permission, one bit shifted to the left by 0, is executable. The executable bit is set to 1, and the right one, that one bit shift to 2 places to the left, is the read, probably. Read-only data just has the read bit, and data will have that bit one bit shifted to the left one time. This is the read write. So we have 3 sections: text, read-only, and data. That text will be executable and readable, read-only data will be only readable, and data will be written, writable, and readable. And about this, we are defining the let's say the assignment between the object files that the compiler will produce and the final ELF executable. So that dot equals 0x 8 zeros and 8 and 7 zeros is just the starting virtual address of our kernel. We are gonna use a higher half kernel, so the higher addresses of the memory will be where our kernel resides, and the dot is the current position pointer. So we are telling the program that we want to define sections from this address, this high address. Kernel start equals dot is just the way to define a symbol in the linker format. So we are creating a symbol that will be accessible by our source code that just points to that current position pointer that actually is right now FFF 8000. And for this, we are gonna define our text and data sections. Text just uses the everything that will be called that text or that text dot asterisk, everything following that. This is a wildcard, and this takes just the output of the every executable object file that the compiler produces, and the compiler will already assign a few default sections. One of them will be text, another data, and another BSS. So for this, we are just gonna define where everything goes, and that multiple dots or two dots text that we'll have there or data is just the mapping with the permissions that we set up. After this, we are gonna create a discard section that just tells us please don't include this anywhere. So you cannot see this, but we are defining a kernel end symbol that will just be the last position of our code. So a quick thing, I'm not sure if I'm gonna have time for this, but you can pause the video. That 1 plus equals constant page size is just a way to align to a page boundary our code, because we want our accesses to memory to be page aligned to make them faster, more optimized. It's just a way to add empty values until we get to a page boundary. And we're creating our underscore start function right here. This is the function that will be called by our bootloader when it calls our ELF, or it loads our ELF kernel. And we are creating a function that will be called print, that will receive a string. And we were going to create another function that will be called string len, for simplifying the print process. We'll have to include our resource.h, and we are gonna implement our print function. Probably we'll let Copilot create it. Okay, so first we are gonna do the print function that will just define a function pointer and call getTerminalWriter that will return our function pointer. So with this, we'll have a variable called writer that is actually callable as just a function. You can do write, open, close parentheses, and pass it a string and a length. But for getting that length, we will need a way to tell how long a string is. So this is where our string length function comes in handy. And for that, we are defining our function called string len that will return a new uint64_t and will receive a string. So for this, I'm gonna just let Copilot do the work for me. Copilot is an awesome tool. So we are defining here a variable that will be increased by 1 each time our string indexed by the longitude, the length is not 0, because our ASCII termination character will be 0, and we will just return that length. So for this, let's see where we are. Why we are now? Okay. Yes, we were probably just checking that this function was right. So for this, we'll just have to include our boot services, not probably nothing else. Just okay. So this could enter an infinite loop if our string was not finished by a 0 null character. This is unlikely, but we'll just check that the length doesn't exceed an arbitrary value that we set on 64k. 65536, and if in case it is bigger, we'll just exit that while loop. And for this, we can already call probably string len, passing it a string. Yes, we are passing it string len as the length value. So this is our print function, and let's just call print hello world, and probably compile and get a lot of errors that we will fix quickly. Because nobody gets to compile first time. Okay, let's create a halt function. That's just that one that you saw for error controlling, just the same, an infinite loop that makes the machine get stuck and not reset. Because when the kernel finishes, the machine will just reboot. We don't want this. We want to enter an infinite loop to be able to check what the machine is doing. So we are gonna create a make build xp that is not the target, that is build just exp without build. Just search for it, figure it out. Okay, just make exp and let's start debugging. So there is a bug there that consists on us calling terminal get terminal count. In this case, get terminal count returns a new in64 underscore t. Just want to compare them. We don't want to call anything, and there is a problem with no such file of directory of linker.ld because the name is wrong. We'll just have to rename it to linker, not link here. Okay, with this, let's go and let's check where it fails. So it is saying that there is no startup.nsh. This is really important because this is the script that enables us to find our UEFI firmware from any drive. This is a code that you should just clone and forget about it. It is not really interesting. This is UEFI stuff. Just copy it to the root of your project. And actually, what I recommend you is just understand this and clone the directory that you'll have attached to make sure that you're building your template for building the kernel is correct and you are not missing any files that will yield a weird error. So this is really boring. It just iterates through the different folders and drives that may contain a firmware file, and if it finds it, it will boot it, and if not, it will go to the next until it crashes because it won't find a bootloader. So you have your startup.nsh, and in this case it's telling us that there is no limine.cfg. This is important. This is really easy. You can just copy it as I told you, and this is just the way to make limine know where the firmware is or the elf file is, and that's basically a .cfg file that you have to include. And this is just telling limine that we don't want to print the boot menu. We are gonna create a section that is called tutos, and our protocol is limine in this case. It supports multiple protocols like multi-boot or group. Group uses multi-boot, but we are using the native limine protocol, and the kernel path. There is a mistake here. This should be boot with two O's. It will fail right now, but we are pointing it to our kernel.elf file. So this is the result of compiling the kernel. So let's say, okay, this is just because the make file is not suited for this project. This was the Bloodmo make file and has a few test files that are not in this project, so we will just delete them. That test.fig file will be deleted. There's another one that it won't find, so in this case is quack.eso. So in this case we'll just gonna delete that -cd-rom flag. Okay, and in this case it will boot, but it will fail to find that ELF file because we have specified it with one O only. So it is calling the firmware, and limine is crashing as it said that resource bot is not valid. So we have messed it up there. We'll update our limine.cfg to include a second O, and now it should boot. And as we can see, the kernel is printing hello world. So this is already working. I'm not sure how much time do I have, so 3 minutes until the video ends. And basically what we have made here is our print functionality. We are one step closer to having a fully functional kernel. And a few quick things before the video ends, because I don't want to have to record this. So if you see any changes that I am making, just follow up, but make sure that you do these steps strictly as you are shown. You will be able to hack it a little bit after, but the foundation is really important. So with this, I hope you guys enjoyed the video. I will be updating this series pretty often, so the idea is to create a um, uh, full memory support. This is virtual memory, paging, memory protection, the heap, probably mmap function, and after this, the second tutorial talks about memory indeed, and a few things about device drivers. We will be able to read from our keyboard, probably having a small network stack, and having support for multiprocess. Will be a multiprocess kernel with full user space support, having device drivers for AHCIs, SM BIOS information gathering, full PCI compliance, and a few more things that I cannot recall right now. This has been a really long video. Following videos will be shorter as I get more used to doing this. You can see my English is not the best. I get better as I warm up, but this is just a voiceover to enable you guys to follow up if you are not Spanish. The Spanish version is more fluent and is recorded over the screen, so there is a direct correlation, which here isn't. And I don't think there's nothing else to tell. You have already available the second part of this video, and I hope you guys enjoy it. Don't forget to subscribe, give it a like, make a comment telling I'm following the English version. Please continue the voiceovers, because if not, I will stop with them. That's pretty much it. Thank you so much, guys, for watching, and I'll see you on the next video. And there are 10 seconds left of this video, so I will count down. So 6, 5, 4, 3, 2, 1. See you!